All right, in this session, we want to look at a few activities on galvanic cell as we try to walk through. While you're doing these activities, it is important that you try to answer questions first before running through the corrections with us. It really tests what you know and what you don't know. So you need to pause the video, answer the questions, and then play the video again to check the activities and the questions that you've answered wrongly, so you'd know where to correct them and apply the corrections in the next question. So we've got this question, and let's see the rest of the question. You need to be able to answer 17 marks all through. So pause. When you finish, you play again, and then you run with us. Now let's answer the questions together. Okay, do we have enough space? Yes, we do. Okay, the potential difference of a galvanic cell measured experimentally by learners is compared with its potential difference calculated at standard conditions. We talked about standard conditions. Remember, we said it's standard, if it's a gas, we talk about standard pressure, 1 atmosphere. Concentration should be at 1 mole per dm cube. And our standard temperature is 25 degrees Celsius, which is 298 Kelvin. Now, the setup is as follows of a galvanic cell. We have that salt bridge. Now, when you get your galvanic cell questions, it is important that you first, before you start answering the questions, let's identify which one is our anode and which one is our cathode. That is the first thing to do. So we need our table to get which one is our anode and cathode. So we're dealing with lead. Now, if you notice, we're dealing with Cu solid and Cu2 plus, lead and Pb2 plus. So we need to go to the table. Let's work with values this, in this session. Let's look for lead. All right, copper is right here. This is copper, positive 0,2, 0,34, and lead, okay, got it, negative 0,13. So lead is negative 0,13, and copper is positive 0,34. Let's go back and then write these values. Don't forget, I'm sure you have your tables, positive 0,34, and so this is positive 0,34, and this is negative 0,13. All right. So now let's work with this together. We said the more positive one will be reduced, easily reduced, because if you go back to the table, let's just get a few things clear so that when we come back to the table, we don't have to waste much time. If you look at this, the arrow here says increase in oxidizing ability, which means Cu2 plus is a stronger oxidizing agent. Therefore, it will be easily reduced. Again, you see our answers just been confirmed, and lead will be oxidized. So copper 2 plus will be where the reduction takes place, while lead will be where the oxidation. A more positive means more reactive. It's a stronger oxidizing agent. It will be easily reduced. So we can go back to our table again because we've already confirmed our answers now. So reduction is going to take place here because it's a stronger oxidizing agent, and oxidation will take place here. So this should be our anode and this should be our cathode. All right. Okay. Now, 8.1. Write down the energy conversion that takes place in the cell. Of course, we know that a galvanic cell would convert chemical energy to electrical energy. And then you have 1 mark, a good place to start. 1 mark there. State one function of the salt bridge. Okay, I'm going to give you 2 in this case. Number 8.2, we know it completes the circuit. All right, and number 2, it maintains electrical neutrality. Maintains electrical neutrality in the internal circuit. And we did explain how that works. That works by the anions moving towards the anode and the cations moving towards the cathode. All right. Number 3, write down the half reaction that takes place at the anode. Okay. Remember which one is our anode? It's the lead. Anode. 8.3, we said anode half cell. Anode half cell. All we need to do, okay, for beginners, we go back to our table. Since it's oxidation, anode, we're dealing with lead. We copy this, we reverse, and we paste, because we said anode is the loss of electron, the loss. So lead, it's going to be lead, and this is solid. You have lead 2 plus, which is aqueous, plus 2 electrons. And then you get your marks there. No hassle at all. You have 3 marks, 2. All right. In which direction do electrons flow in the circuit? Remember that electrons, there's electron loss here, and there's electron gain here, because that's how we define reduction. So electrons are moving from where it is lost to where it is gained. So it is from PB to CU. And we're done. 1 mark, okay. All right, 8.5. Write down the balanced overall cell reaction. Now in answering 8.5, we're going to need this as well. So 8.5, can I just write the cathode here? Cathode will be Cu2 plus 2E to give us what? Copper solid. That is reduction. Reduction of copper, the gain of electron. Now all we need to do is to add what's on the left to the left. On the left, we've got Pb solid plus Cu2 plus aqueous, and that will give us on the right, we have Pb2 plus aqueous plus Cu solid. And that gives you 3 marks because it's balanced. Remember our electrons, we've got 2 electrons, and then we've got 2 electrons. So the electrons cancels out, and then we're balanced. All right. Is this cell reaction exothermic or endothermic? All right, it will be exothermic, and that is simply explained because reduction and oxidation are taking place at the same time. And you would see later on when we calculate that we are going to have a positive E cell value, a positive potential difference. So because oxidation and reduction are taking place, we have the cell to be exothermic. It is spontaneous. That's another way to explain. It is spontaneous, so it will always give out heat if it is spontaneous. Exothermic reaction. Use the table now to calculate the standard potential, to calculate the potential difference. Already we have our values up there. If you remember, we have negative 0.13 and 0.34. What is our formula? Our formula, okay, we need to move this down a bit to allow us have space. All right, we need space here. That is 8.7. How do we calculate? We need to go back to our formula page. Let me show you where the formula would be. All right, here's our formula here. Let's clean this. Here's our formula. You have your E. Any of these formulas would actually work. So E cathode, since we know our cathode and our anode, we can easily use that. So our E cell will be E cathode minus E anode. Remember what our anode is, and our copper is the cathode. This is 0.34 minus negative 0.13. All right, if you do that mathematically, we should have positive 0.47 volts. And then you get 4 marks. 4 marks. You have 1 for the formula, your substitutions, and then your final answer. I think there's a 4 marks that everyone watching this video should get in an exam. From the results obtained, the learners conclude that the measured potential difference differs from the calculated potential difference. Give 2 possible reasons for your answer. Okay, the table we used were tables, were values gotten from standard conditions. So in this case, the possible option or possible answers would be that the experiment was not done at standard condition. But we must write the standard condition of concentration of 1 mole per dm cube and the standard temperature of 298 Kelvin. Capital K there. All right. So if it is not done at standard conditions, then we're going to have a different value. Now that's 17 marks done there for you. I think that should help you answer the next question. So we go to the next question right now so that you again can start answering the question, and then you walk through. When you walk through, we'll be able to walk through together. All right, let's make sure that this is very visible for everyone. Okay. All right, so you need to answer these questions. Remember to pause the video, answer the questions, and then we will be ready to go. All right, let's go. The cell notation of a standard galvanic cell containing an unknown element electrode X is shown below. All right, we have that. What this should instantly tell you that this is the anode. Okay, sorry about that. What this should tell us instantly is that this is the anode. Remember, the cell notation is written as A, B, and C. All right, so the anode, the bridge, and the cathode. Very important point to know. Name the component of the cell represented by double lines in the above cell notations. Salt bridge, 1 mark. That's your salt bridge. All right. State the 2 standard conditions that are applicable. We said that just a few minutes ago. The standard conditions. You have your standard concentration of 1 mole per dm cube, and standard temperature of what? 298 Kelvin. Remember, we cannot use pressure here because pressure is only applicable to gases. Identify the oxidizing agent in the above cell. The oxidizing agent is actually what is reduced. And reduction takes place at the cathode. So our lead here is where reduction takes place. So our answer should be lead 2 plus. Lead 2 plus is what is reduced to lead. All right. So our oxidizing agent is lead 2 plus. Another mark there. The initial reading on the voltmeter connected across the electrodes of the above cell is 1,53. Identify X by calculating the standard reduction. Remember, our cathode is there. So again, we need to do our calculation. We have E cell equals to E cathode minus E anode. Remember, this is X and this is lead. But we do have this value giving us 1,53 spontaneous because it's a positive value. What is the potential difference of the half cell, lead half cell? Let's go back to our table quickly and find lead. I'm not sure if we used it earlier on. Yes, negative 0,13. I'm sure you have your tables. Negative 0,13 equals to E anode. All right, so if we calculate well, bring this one over to the other side, it becomes 1,53 plus 0,13, and that is negative E anode. And what will that be if you use your calculator? It will give you 1,66 as negative E anode. All right, simple mathematics now. This multiply both sides by negative 1 so that our E anode becomes negative 1,66 volts. So we go back to our table and check for negative 1,66 because we're trying to identify the element. Negative 1,66, here it is. All right, so our element is aluminum. So our X is Al, aluminum. All right, good question there. Okay, good question. All right, so write down the balanced equation for the net. Again, we need our, since we already know aluminum, remember aluminum is the anode, so the easiest way now is to say what happens at the anode. It's oxidation. We're going to have Al, remember it's losing, it's Al3 plus 3 electron, and then at the cathode, remember what we have lead. Remember, is it lead? Yes. Cathode is lead. So it's lead 2 plus 2 electron, giving us lead solid. All right. Now remember here, it's a bit different from the first one. We need to balance our electrons. How do we balance? We use these to balance. So we need to multiply this equation by 2 and multiply this equation by 3. I'm going to write it out for now so that it becomes clear. If we multiply all this by 2, it's going to be 2Al, and then we have 2Al3 plus 6 electron, while on the other equation 2 we have 3Pb2 plus 6 electrons to give us 3 lead solid. Then we write down now our electrons are balanced, 6 electrons, 6 electrons. So we have 2Al, which is a solid, plus 3Pb2 plus, which is aqueous, would give us what? 2Al, 3 plus again, which is aqueous, and you have 3Pb, which is lead, and that's solid. And that is done. So we must learn how to balance our equations. I hope this is all right and simple enough for us to run through. Okay, how will the voltmeter reading be affected if the concentration of the electrolyte in X is increased? All right, this is just a content question. If we increase the concentration, remember it is no longer standard now. If we increase this concentration, it means, oh my God, all right, it's E anode. If we increase the concentration here, it means there are more electrons available. If there are more electrons, the difference between the cathode and the anode now becomes very small. So the potential difference will decrease because there are more electrons than normal on the anode, in the anode of cell, which reduces the potential difference. All right, write down the value of the reading on the voltmeter when the cell has reached equilibrium. This is our Le Chatelier's principle. When it has reached equilibrium, it means there is no more deficit and there is no more excess electron. The value of the potential difference simply becomes 0 volts. We explained that when we said the cell is flat. This is what happens, Le Chatelier's principle. Another 16 marks, very good to get. All right. Now let's run through the next. Let's run through the next, please. You need to rewind these over and over again. Re-answer the questions when we're done so that you have a good understanding of what this is all about. Okay, here we go. I love this. And another question 8. Remember to pause the video, answer the questions, and then, all right. So let's get on to answering these questions now. The other side of the question, here we go. All right, so that we can have all the questions answered. All right, let's start answering the questions. I believe you are done. You are done answering these questions. It is very important that you answer the questions. It helps you to understand what's going on. Okay, now let's read the question together. The voltaic cell represented below functions as standard conditions. Again, so by now we should be able to know what the standard conditions are. Write down the concentration of the hydrogen ion in the 1/2 cell. Since the set standard conditions, our standard concentration should simply be 1 mole per dm cube, and we're done because it's standard. 1 mark. Just testing your content. 1 mark there, which is very easy to get. All right. Solid present in the half cell are usually used as electrode. Give a reason why iodine solid is not suitable. Iodine is a non-metal. It will not conduct electricity. So that's why you remember we said electrode is simply a word gotten from an electric rod. So solids are not, non-metals, iodine, cannot conduct electricity. So that's just our answer. Iodine is not a conductor. It cannot conduct electricity. Hence, we introduce an inert electrode called graphite, which is carbon. All right. Write down 2 properties of graphite other than being a solid that makes it suitable. All right, so graphite, it is inert. It will not react, because if it reacts, it will cause a disbalance in the chemical composition of the battery. It is inert, and number 2, it is a conductor of electricity. Conductor, all right, it's a good conductor. Remember, carbon can behave as both a metal and a non-metal. So those are 2 reasons why we use graphite. It is inert and it is a conductor of electricity. Number 8.4. From the above voltaic cell, write down the name of the oxidizing agent. Again, we're looking for what is reduced. Now, I want us to see something here. We've got quite a number of things here. We've got our permanganate ions, we've got manganese, we've got hydrogen, so we need to carefully find out which one will be oxidized and which one will be reduced. Let's go to our table and pick all these values. Remember what we are looking for. We're looking for, okay, already we know hydrogen is 0, all right? Let's look for Mn. All right, I found Mn2 plus. Mn2 plus is negative 1,18. So that we don't forget, I'm going to come down here and write all the values we have. We have Mn manganese, positive 1,18. Remember, we now need, again, we need permanganate ion. Let's find that somewhere there in that table, permanganate. All right, I got it. Positive 1,51. What else do we need? Iodine. Let's find iodine there. Here we have iodine, positive 0,54. Actually, we should have iodine as positive 0,54 and hydrogen is just 0. Now, what do we know? We know that the most positive is always going to be reduced. And here, this permanganate seems to be our most positive. So it's going to be our oxidizing agent. So if we need to write the formula of the oxidizing agent, we go back to the table, and this is what you find on the table. Oh, the question says first, we've identified that. All right, name of the oxidizing agent, name. So we must know the name. It is our permanganate ion, because that is what is oxidized. Sorry, that is what is reduced. So it is our oxidizing agent. Remember how we got that? The most positive value becomes reduced, which is our oxidizing agent. Now, the next question says we should write down the net cell reaction. Remember, the net cell reaction is simply the cathode half cell and the anode half cell. So let's quickly write down what takes place at the cathode, and let's write down what takes place at the anode. Our permanganate is reduced, so we need to go back to the table. Let's go back to the table. Let's go back to the table and find what to write. This is what we have. It's MnO4 minus, I'm sure you have your table, plus 8 hydrogen plus 5 electron, and then we have Mn2 plus 4 H2O. We need to write that down, as our anode, as our cathode. Remember, it is gaining. So all we do here is to copy and paste. So it's MnO4 minus, and that's at our cathode. Let me use a different ink just to, it's MnO4 minus, all right, let's walk through, plus 8 and 5, plus 8 hydrogen, plus 5 electrons. And what are we going to get from that? Mn2 plus 4 H2O. Mn2 plus 4 H2O. What about our anode? Our anode is iodine. And what do we have? Remember, we copy, reverse, and paste. It's 2I2, I2, and then 2E. So we go back there, 2I2 there, and then we have I2 plus 2E. All right. Do you notice, let's just confirm that we have the correct thing. I2 plus 2E, and then we have 2 there. Good. Now, do you notice that our electrons are not balanced? We need to balance our electrons by multiplying this by 5 and multiplying this by 2. Let's do that together very, very quickly. It's going to be 10 iodine ion plus 5 I2 plus 10 electrons. And then on the second equation, we have 2m. Okay. Let's sort this out quickly. All right, it's 2 MnO4 minus plus 2 times 8 gives me 16 hydrogen plus. Can you see that our electrons are now automatically balanced? 2Mn2 plus 8H2O. Now what do? We write what's on the left to the left, and then what's on the right we keep to the right. What do we have here? We've got 10I plus 2 MnO4 plus 60. Now we don't need to introduce our electron because it automatically cancels out. All right, balancing chemical equation. But if you notice, all our coefficients are even numbers, so we can divide all through by 2 so that we have 5I, remember this is aqueous, plus MnO4. Remember this is permanganate ion there, so we need to write that permanganate ion, plus 8. We're dividing by 2 because it must be written with the lowest coefficient, plus 4H2O. And we are done. That's how to work through. Please remember always to leave it in, as simple, in a simple form as possible. All right, let's run through to make sure that we got it right. We got it right. Let's check something on our table quickly, just to make sure that we got it right there. All right, it's MnO4 there. Good. And then we come back here just to make sure that we get things right. Oh, wait. Okay. We have 10, and we have, let's just confirm if we have everything. We have 10, we have that, we have 16. Oh, we missed out our 5. We missed out our 5I2. So we cannot divide by 2 because we have an odd number there. Remember, our odd number will stop us from dividing by 2. So this is what we should actually have. We omitted our 5I2, so this is what the final answer should look like. Remember, it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 elements. All right, and that's our final answer. Okay, we had omitted this earlier on, but it should be there, 5I2. So this is 5, 8, 2, 16, 2, 10. We cannot divide that by 2. All right, same process, same tactics all along. Let's look at the next question. The cell notation. Our cell notation, remember our cell notation is as simple as A, B, C, the anode, the bridge, and the cathode. All right, remember we have already identified our anode and our cathode. Our anode is where the iodine is, and our cathode is where the magnesium is. But we are using graphite electrode. So in this case, there's a bit of a difference. We must start with carbon as the electrode. Remember the other ones, we would write that. And then now we would write our I, which is aqueous, which is now changing into I2 solid. All right, and we have our salt bridge. We need to write everything we find in the half cell, separated by a comma, everything we have in the half cell. MnO4 minus, all right, which is also aqueous. And then we have Mn2 plus, which is also aqueous. Again, we have our graphite electrode. So this is a bit of a difference here. And let's go back. I want to show you something quickly. You know, we said this is the anode and this is the cathode. Could you imagine if someone were to walk down here? Okay, let's have this guy who's walking down here. This guy is going to walk right on this and work into this. All right, so it starts from the graphite. That's how we write it, ABC. Walks down here, it swims in this solution here, and then finds its way onto the salt bridge. Okay, finds its way onto the salt bridge, and gets here again, thinking it's over. It slides again and comes to this, comes to this, comes to this, and slides out. That is the path of, so it's like we're writing the path this guy would go through. This guy would start from carbon, then he would come into your I minus, and then your I2, then gets to the salt bridge. Now it comes down, it finds hydrogen, it finds your permanganate ion, finds your manganese ion, and then gets back onto carbon. So that's how the salt bridge is written. It's the anode, the bridge, and the cathode. Remember, we introduced inert electrode in this case. All right. Now, calculate the cell potential of the above cell. Again, we deal with our anode and our cathode, and the formula just remains the same. E cathode equals to, E cell, jumping the gun, E cathode minus E anode. And we already know our cathode. Remember, we wrote the values down when we started. 1,51 minus 0,54, and our answer becomes 0,97 volts. It's a spontaneous. Remember, we wrote down the values. Let me just confirm. You see, we have this as the cathode and that as the anode. And the difference is 0,97 volts, spontaneous. Good. So that's another 4 marks there for you. How will the reading on the voltmeter? Now, this is a repeated question. How will the reading on the voltmeter be affected if the concentration of MnO4 decreases? Write down only increase, decrease, and remain the same. All right? MnO4. Now, they've just switched this question all around the other time. The other time it was the anode, and we said it would decrease. Now it's the cathode. The cathode decreasing. If the cathode decreases, the potential difference between the cathode and the anode will also decrease, because there is less difference in the excess electron and the deficit electron, because now we are having less electrons at the cathode, so which is very close in number to that of the anode. So our answer should decrease. The potential difference would what? Would decrease. And you have your mark again. There's 16 marks again, right in your pocket. I believe you're getting this well as we go on. I think we do have, all right, we do have one more. We do have one more for this session. All right, you remember what you need to do. Answer the question. When you answer the question, now you are able to work with the corrections with us. Okay, the second part of the question. So we have that table now, and then that. Okay, now let's start answering the questions together. So you are done with the question. Okay. Consider the following half reaction. Okay, we're given this as a half reaction. All right, we're given this as a half reaction that we need to deal with quickly. We have a solution of potassium dichromate. A solution of potassium dichromate now is added to oxalic acid. So what we have actually up there is oxalic acid. What we have up there is oxalic acid. Now we have a solution of potassium dichromate added to that. Explain why the reaction between the solution of oxalic acid and potassium dichromate will be spontaneous. Refer to the strength of the oxidizing agent and reducing agents in your answer. Why will this be spontaneous? Why should our E value be positive? All we need to do first is to find, okay, look at this. We are given this value, we are given this value. We're given the value of oxalic acid. Okay, let's go down and put that somewhere. Oxalic acid is negative 0.49. Oh, okay. We need a new page to allow us space. All right, negative 0.49 oxalic acid. So the oxalic acid, the potential value is negative 0.49. Now we need to go to the table and find dichromate. Okay, let's go back so that you know what we're looking for. Dichromate is, we're looking for this, 2 chromium. Now let's go to our table and find dichromate. Here we have the dichromate. It's 1,33, positive 1,33. All right. So dichromate. All right, this is more positive, so it will be reduced, and this will be oxidized. All right, so in answering this question, we already see that the half reaction, the value here of oxalic acid is actually lower than this. Once we have a difference, then we know that it will be spontaneous. So what should our answer be? Let's see. We can say that oxalic acid half reaction has a lower E value, has a lower, all right, than the dichromate one. All right, therefore the dichromate, because then we should refer, remember the question says refer to the reducing the strength, strongest oxidizing agent, or is a stronger oxidizing, since we're dealing with 2, as a stronger oxidizing agent, therefore will be what? Will be reduced. So already we have oxidation and reduction taking place, while the oxalic acid will be oxidized. So because of that, oxalic acid will be oxidized. Because of this, it is spontaneous because they are both reactions are taking place. Or another way we can explain this, you remember, is to say that E cell equals to E cathode minus E anode. Already we know what to be oxidized and what to be reduced. So it's going to be 1 minus 1,33 minus 0,49. This is another way, positive 1,82 volts. Because it is positive, positive means it will be spontaneous. Remember, the more positive is reduced. So here we have reduction, and here we have what? Oxidation. All right, in case you cannot explain it in words, you can just simply do your calculations and you get your answer. So it's 1 mark there, it's 1 mark there, and this positive and spontaneous gets you your other math. Very, very straightforward. All right. Let's look at the next question. I'm glad we're looking at different questions just to help us understand and get ready for exam. Use half reaction to write down a balanced equation for the reaction between oxalic acid and potassium dichromate. Leave your answer in the ionic form without spectator ions. Okay? Again, we write the anode and we write the cathode. All right. Now, which one is the cathode? The reduced one, which is our dichromate that we can get from the table. It's Cr2O7 minus plus 14, which is what we have there, plus 6E. I'm sure you have your table, so we can write that as our cathode. It's Cr2O7, 2 minus, plus we have 14 hydrogen there, plus 6 electron, and we have 2 Cr. We're just copying what we have on our table. Now, at the anode, what do we expect? Oxalic acid. Let's go back and check what we're given in the question for oxalic acid. We're given the half reaction. All right. So we need to write that, and then, but our electrons need to be on the right hand side. Sure, we've written that down somewhere. So we should have H2C2O4, 2CO2 plus 2 hydrogen. Is that okay? Let's write this clearly, because that's what we have there. Plus 2 hydrogen plus 2 electron. Remember, our electrons need to be balanced. And to balance this, because we need to make this 6, I think we can just simply multiply this by 3. All right, if we multiply this by 3, because 2 times 3 will give us 6, then we do not have to do so much calculations. All right, can I just do this here? If I multiply this by 3, 3 times, instead of writing this, okay, let's write it. It's 3H2C2O4 to give us 6 carbon dioxide plus 6 hydrogen plus 6 electrons. So I'm going to deal with both reactions now at the same time. Now I'm working with this. I'm working with this. All right, so what do we have on the left? We have this, remember? We have 3 of them again, so that we don't leave anyone behind. 2 minus, plus 14, that, plus 3 H2C2O4, and here we've got 1, 2, 3, 4 this time around. 2Cr3 plus 7 H2O plus 6 carbon dioxide plus 6. Okay, now let's see. But if you notice here, we've got hydrogen and hydrogen. We need to bring them together. If we move this over to the side, it becomes negative. So our final answer, therefore, should be, because we cannot have 2 hydrogens on that equation there, it needs to be balanced. Final answer will be Cr2O7 2 minus plus 8 hydrogen. Where is that 8 coming from? 14 minus what? 6 plus 3 H2C2O4, and that should give us 2Cr. Sorry, this 3 should actually be up there. 3 plus 7 moles of water plus 6 moles of carbon dioxide. Great question. Good answer. All right, same process over and over again, repeated. All right, if you miss anything, you can repeat and rewind. That's the advantage of this kind of sessions. All right, now let's move over again to the last session of this question. A learner sets up a standard electrochemical cell using the following half reactions. All right, we've got platinum here. We've got platinum, okay? And platinum, we use platinum as an inert electrode when we use a gas. And you can see we have oxygen gas. And that's why we use a platinum. Remember the reason? It's a solid, conducts electricity, and it's inert. And you have potassium chloride is used in the salt bridge. So we have this. Which half cell, A or B, contains the cathode? Again, we need to check. We have Cu2 plus and we have oxygen. Remember what we have here? Hydrogen peroxide. Let's go back to our table and check for hydrogen peroxide, the value of hydrogen peroxide. All right, here we have hydrogen peroxide, but this is water. Let's see. We need oxygen. You need to go up and down the table to find the right value. It is possible you'd miss it, but you need to keep checking until you find the correct one. Okay, here we go. We found it here because it is oxygen, and the value here is positive 0.68. Okay, positive 0.68, and we're comparing that with copper. Remember, it's copper solid again. Positive 0.68 and positive 0.34. 0.34 here and positive 0.68. The more positive will be reduced. So we have reduction taking place here, and therefore this is the cathode. Anode and oxidation. So which half cell, A or B, contains the cathode? It's B. Write down the oxidation. Now they want us to write this oxidation. We've been writing these over and over again. Oxidation. Okay, we'll need to go down a whole lot here. Oxidation will be Cu, all right, Cu2 plus 2E. And you get your 2 marks, as you know, very swiftly and very easily there. The next one is write down the cell notation for this cell. Cell notation, remember, is different from your ionic equation. Cell notation is the one we say anode, bridge, and cathode. Now remember again, if somebody was to walk down, we start from the anode. This guy is going to slide down. It's Cu, Cu2 plus. We have the salt bridge. This guy walks over there. Now slides down again on the salt bridge and gets into this equation, all right, which is H2O2 there. And also we're going to have hydrogen here, we'll see from the table. And then this guy, remember oxygen gas is also involved here. And this guy climbs out through the platinum. All right, I want us to copy quickly what we have on our table where we got the 0.68 from. All right, you see it's H2O2, O2, 2 hydrogen, and 2 electron. Okay, so we see that these guys are involved. These guys are involved, and this guy is also involved. So again, we start from the anode, the bridge, and we run through to the cathode. Our anode, the guy started sliding down from Cu, solid. We have a phase change. We have Cu2 plus. Remember, it's aqueous, 1 mole per dm cube. We have our salt bridge. And then in the equation, we have H plus. Remember, we write everything. In this case, the examiner wants you to be able to identify what's in the half cell. We have oxygen gas because that's the main supply there. And then we have, remember, The guy is climbing out on a platinum electrode, inert, solid, and a conductor of electricity. That's our half cell reaction. Quickly there. All right. Half cell reaction. I want to believe this is getting easier. In the next session, we'll have about 6 exercises to work with. The potential difference of the cell. Remember, we have our values. We wrote down our values. We have 0.68 and 0.34. I think once you do that, you've already answered your question even before you read the question. E cell, again, is E cathode minus E anode. And our cathode, you have the 0.68, that's the oxygen half cell. And here you have 0.34, and our answer should be 0.34 volts. If you use your calculator, it is spontaneous because it is a positive value. All right, the last question here. After several days, the reading on the voltmeter is 0. Explain why this. Again, we come to our Le Chatelier's principle. And let's just write this in bullets quickly. Remember that the concentration change causes a stress. And what is really happening? The reactant concentration of the reactant ion decreases as the concentration of the product ion increases. You remember that. That's the stress in the system. What will now happen? The equilibrium shifts to favor the reverse. To favor the reverse reaction. All right? To favor the reverse reaction so that the concentration of the reactant ion begins to increase in such a way that the rate of the forward is now the same with the rate of the reverse reaction. And once you have this rate of reverse reaction equal, already we have our dynamic equilibrium. What happens? The E cell value becomes 0. There is no 0 volts because there is no potential what? No potential difference anymore. There's no deficit and there is no excess because the rate at which the electrons are transferred forth and back is now the same. No potential difference, no current flows in the circuit. All right, we've done this question quite a number of times. The explanation is just the same. Let me help you quickly with an explanation here. If we say A plus B, we have C plus D. Okay, now in this case we have this concentration decreasing, which means the concentration of this is increasing. The forward reaction is favored. Now that's a stress. The system will work in such a way that it balances the stress by allowing the reverse reaction to be favored. All right, when the reverse reaction is now favored, B will increase, and this will continue until the forward and the reverse reaction happen at the same rate. Hence, the rate of oxidation is now equal to the rate of reduction. Hence, we have no excess and no deficit electron. on both sides because they are transferred at the same time. As it's going this way, it's also moving that way. All right, so there is no potential difference between the forward and the reverse anymore. So our potential value, a difference value, becomes what? Zero, because the rate at the cathode and at the anode now remains the same. I want to believe these activities will help you understand more. Check the next video. We do have more questions to help you understand. Remember what you need to do. You need to answer the questions and then mark yourself as we do the corrections. Anyway, it's an honor to serve you again. This is Bishop signing out on behalf of Crazy Physics. You can always reach us again on 078 071 7507. Principals can give us a call and we will help your learners to get through understanding physical science a lot better. Thank you.